Welcome to the video for C2.2.8 where we're going to look at the structure of metals. So our learning objectives for today, you need to be able to describe the structure and bonding in metals and relate that to their properties, and then have a look at the limitations of different models of metals. So keywords that we need to know. So delocalized electrons. So electrons are normally associated with atoms, but sometimes they can become delocalized, which means they're not tied to a certain location. So they're not in an atom. They can freely move. Giant metallic lattice. So we've met the word lattice before when we've looked at ionic lattices and giant covalent lattices, which are just repeating regular arrangements. So a giant metallic lattice is where we've got metal atoms or ions in a metal in the solid state. And metallic bonds, we're going to look at metallic bonds today. So metallic bonds are the strong electrostatic forces of attraction between the delocalized electrons and the metal ions. So what you need to do is pause the video, copy this table, and then write down what use each of those metals will have based on their property. So you're quite often asked in exam questions to link the property of a material with its use. So this is just a bit of practice of that. So pause the video and then I'll go through the answers on the next slide. Okay, so aluminium is a good heat conductor, and because it's a good heat conductor, it can be used in radiators. So brass is sonorous, which means it makes a nice ringing sound when you hit it, so we can use it in church bells. Copper is a good conductor of electricity, so it's used in electrical wires. Steel is ductile. Remember, ductile means it can be drawn into long, thin wires, so it's used in paper clips. Silver is reflective, so it's used as the backing in mirrors. Titanium's got low density, so it can be used to make aircraft bodies, because you want the aircraft to be as light as possible. So you want to use a low density material so that you don't need to waste fuel putting that aircraft up into the air. And lastly, stainless steel, that we should know all about based on where we live, is malleable, which means you can make it easily into lots of different shapes. So it's used for cutlery. Okay, so let's just quickly think back to the bonding that we've already met. So ionic bonding is between a metal and a non-metal. So you get positive ions and you get negative ions. So the metals form positive ions because they've lost electrons, and those electrons are transferred to the non-metals, which become negative. And it's a giant repeating lattice of those ions. So there's electrostatic attraction between the positive and negative ions in all directions, which is why it's a very strong attraction and why you've got high melting points. So it's a giant lattice structure. Covalent bonding, we've looked at two different sorts. So all covalent bonding involves sharing of electrons, because a covalent bond is a pair of shared electrons. It only involves non-metals, because non-metals want to gain. And we've looked at simple covalents, which is small molecules, such as water or carbon dioxide, right through to the giant covalent structures, such as diamond and silicon dioxide. We've also looked at polymers as well, which are kind of in between. They're still molecules, but they're smaller than giant covalent, but they're a lot bigger than simple molecules. So both types have in common is that when they're forming the ions or forming the covalent bonds, what they're trying to do is get a full shell of outer electrons. So for metals, that's by losing electrons, and by non-metals, that's gaining electrons. Okay, so they want to have a full outer shell. So the metal atoms need to lose electrons to get a full outer shell. So those electrons have got to go somewhere. So in ionic bonding, it was easy because those electrons were given to a non-metal which wanted to gain electrons. So it all worked out nicely. But if you've got just metal atoms, then there's no atom that those electrons can be given to. So instead, they become delocalized. Right, there's a video that you can watch here that I recommend you watch. It's a lot more professional than mine. So I'd pause this video, watch that video, and then come back. So in metallic bonding, we're going to look at where it's just metals. So in ionic bonding, we know that we've already met that metals lose electrons to form positive ions, and that's to get a full outer shell. So in metallic bonding, the electrons don't have any atoms non-metal atoms that they can go to, so they just become delocalized. So you get this sea of negative charge that just flows around the positive metal ions. And there's a strong attraction between those positive metal ions and the sea of delocalized charge, and that's the metallic bond. And that's what causes metals to have high melting points, because it's a strong attraction between the positive metal ions and the sea of the negative charge. So you need to pause the video now and copy this diagram and label it with the metal cation and the delocalized electrons. So let's just get my pen up here. So these circles with positive charge in the middle are the metal cations, and these circles with the negative charges in are the delocalized electrons. So it's important that we call them delocalized electrons and not just electrons, because you can see they're not associated with the metal ions. They're free moving. Okay, so these can move, and because you've got charged particles that can move, that means it conducts electricity. And then between these two is a strong attraction. So I wouldn't copy down, the only notes that I would copy down is the metal cations labelled and the delocalized electrons. I'm just trying to explain what this bonding means so that you can answer the next task. So there's a strong attraction between the positive and the negative ions, and that means that most metals have got high melting and boiling points. You probably know the exception to that. So mercury is a liquid at room temperature. Most people know that. And some of you might know that actually gallium, even though it's a solid at room temperature, it's got a low melting point. And actually, if you place it in your hand, it will actually melt. So your body heat is enough to melt that gallium. But most metals have got high melting points. And because these are in layers, they can slide over each other. So the layers of positive ions can easily slide over each other. And that's what makes metals malleable and ductile. So not only can they slide over each other, but there's also the strong attraction between the positive ions and the delocalized electrons. Holds that in place when it happens, so it doesn't fall apart while the layers are sliding over each other, because you've still got a strong attraction between the positive ions and the delocalized electrons. Right, so once you're ready, you might need to pause the video there. Go on to the next slide. Right, so now you need to match up the properties, which are labelled P with the reason for them. So pause the video and get this done, and then I'll go through the answers. Right, so let's go with good conductor of heat or electricity. So let's call this number 1. So the good conductor of heat or electricity is because the delocalized electrons are free to move around the structure. Okay, so the delocalized electrons, because they can move, you've got mobile charged particles, so it can conduct electricity, and also they can carry the thermal energy as well. Right, so the other reasons we've got, so the metal atoms can slide over each other. The bonds in metals don't break easily. The bonds in metals are very strong. So high melting and boiling points, let's call that 2. So they've got high melting and boiling points. So the reason for that is that the bonds in metals are very strong. And the bond, so the metallic bond, is the attraction between positive ion and the delocalized electrons. Right, so we've now got, so malleable is because the bonds in metals don't break easily, so you can bend it into different shapes without them breaking. So that links in with it's strong. So really you could have the bonds in metals are very strong as the same reason. And then ductile can be stretched into long thin wires, is the atoms can slide over each other. And that shouldn't say, actually I don't like that explanation now, so I'm just going to remove that first bit of it there and just say the atoms can slide over each other. And actually I prefer it if you say ions, because they've lost the electrons to become delocalized, so the metal ions can slide over each other. Right, so here's some real exam questions you can have a go at. So pause the video, answer these, and then check your answers on the next slide. So give the electronic structure of sodium and then draw a diagram to show the metallic bonding in sodium. Okay, so the electronic structure of sodium. So if you look in the periodic table, sodium is 23 and 11. I think, in fact, in your periodic table, it's the way around, isn't it? So it's 11 and 23. So we've got the atomic number is the number of electrons, so it's got 11 electrons. And hopefully we can remember from previous videos that the first shell holds 2 electrons, and then the other ones hold 8. So 11 electrons is going to be 2 in the first one, 8 in the second, and then we've got 1 left over, so it's going to be 2, 8, 1. And then draw the diagram to show the metallic bonding in sodium is just the diagram that we copied down before. So it's there's only 2 marks for this, but you need all 3 points to get you 2 marks. So you need the circles with positive charges inside, you need those circles in nice neat ordered rows, and you need the electrons scattered between them. Okay, the next question's a bit more detailed. So this is a 6-mark question. So it's asking you to compare copper and titanium. It's got their uses there, and then you've got to describe how the properties of copper and titanium make them suitable for these uses. So pause the video, and then we'll go over the answer on the next slide. Okay, so if we think about electrical wiring, we're going to need, so it's in long thin wires, so we want it to be ductile, and we want it to conduct electricity. So we want it to conduct electricity well. If we've got water pipes, we want it to be unreactive because we don't want it to react with the water. And we also want it to be malleable because we need to bend it into shape. Saucepan bases, we want to be a good conductor of heat. It's important if you're talking about a good conductor to say whether it's heat or electricity. And we'd also want that to be malleable because we need to bend it into shape for the saucepan. If we want jewellery, we want it to be shiny. We want it to be unreactive because we don't want it to change into something else while we're wearing it as jewellery. And we probably want it to be malleable as well, so we can bend it into shape. Right, titanium, so hip replacements, we want that to be low density because we've got to lug it round all the time, and if it's high density, then it's going to take a lot of effort. We also want it to be unreactive because we don't want it to corrode while it's in our bodies, and we want it to be malleable so we can bend it into shape. Rotors on helicopters, so we'd want that to be low density and malleable. You're going to get a lot of air resistance, so I would suggest that we'd want a high melting point for that as well. Ooh, which reminds me, we've missed that off here. So the saucepan base, we also want a high melting point, don't we? Because we don't want it to melt when we put it on the cooker. Pipes in chemical industry, so just like the water pipes, we want them to be malleable and we want them to be unreactive. Okay, so the official mark scheme's on the next slide.